Hello, everybody. So we are getting very near the end. Tonight starts module 7 of 8. So I'm gonna talk here in a moment about that thing I mentioned last week. It's been a long time coming. I don't make policy changes because of like one instance. I shouldn't say that because one of the ones I was going to mention that's in my notes was a policy change that happened over an instance. What is that? So, well, I'll talk about that in a second. First off, what's on top for us tonight? We want to talk about hash tables and binary trees. Those are the last big data structures that we're talking about. We saw linked lists where we have a bunch of pointers going to the next thing. And making our own linked list. And then we'll have an example on Thursday where we see it. Because obviously linked list, stacked queues, hash tables, all the stuff that we're seeing is built into the Java programming language. The reason we would build our own is because one's built into the language are one size catch all fit every need. So from Thursday's example, we'll see that. The one thing about these, it confuses everybody at this level. First get introduced to data structures, so like confusing, overwhelming. It's like, why would we do that? It's one of those things 10 years from now, you'll think back and be like, oh, that's why Chris said we need to focus on this. So it's not immediately apparent how these are going to come into play. So hopefully the example on Thursday will put that out. The two tonight that are pictures on the board, the hash tables, and we'll do a binary search tree with like 3 methods. We might do an add method, one of our 3 main traversals of the tree. But again, it's built into the language. So we can use the one built into the language for now, as long as you know the basic idea, what the picture looks like. So 10 years from now, when you're the lead developer on a software project and it's your responsibility to decide what's going to happen, then it'll make more sense. Hash tables and binary trees, kind of a lot of things fall back on them. We'll talk briefly about what a heap is. It's such kind of binary search tree, so we got to talk about binary search tree before we talk about what a heap is. Then graph, which is another modification of binary search trees. I have a note that I realized over the weekend I was making a bunch of notes. This is actually the second thing. The changes coming stuff topic, but I do have a note that sometime soon I'll put it in. I'll read all of the upcoming notes for the agendas each evening. That we need to make a call object with ChatGPT. We haven't done that yet. Chatbots can't do the logic. They can't come up with the algorithm, but they can print those the test scores really, really easy. Remember we got that animal object, abstract animal object. We could just ask ChatGPT for an abstract animal object with those 3 fields we had, and we would have the code quicker than we could get that generated over and over and over again like we did, right? We had to type 3 data fields, and then we kept hitting alt insert, which for Mac users I believe is a function insert. It might be control insert. One of those next to command. If you have a bulb in NetBeans, it should tell you what the keyword is. So there's that. But we haven't seen the chatbots, and I am a big fan of having those things write code, because making typos is a human trait. And you don't want to ask that for your entire piece of software. You want to ask for it in little pieces at a time and then copy and paste them together to the real. So I'm going to look at that and realize we haven't done that. So that's on there. Math will be the last of the data structures we're going to look at. And that's what's in your homework this week. So for the 4th week in a row, we're going to do something in class that is exactly what the homework that's due next week, the homework for module 7. For the 4th week in a row, and that's part of getting into the next topic of several people, we've even talked about it, have been in class working on the homework let me know they're working on the homework and all, and that's fine, but they're working on the previous week's homework. And while we are going over this week's homework, so then you miss the example for the upcoming homework, and then that puts then the product. A good way to get stuck in a repeating cycle, if that makes sense. So that's what the policy change was about. I noticed it suddenly, but it was not shortcoming. I guess one more note here, the tutoring coordinator, this is for the future. The new tutoring coordinator had an idea to encourage people to come in. So everybody that comes in is going to get their own custom coffee mug. She's going to have you go Snapchat, print out a Bitmoji from the Snapchat app. And she's going to put that on a coffee mug with your name to encourage people to come in tutoring and stuff. So I believe that's going to start very, very soon. I don't know when it's going to start, but for attending tutoring here on campus, you'll get your own coffee mug that's kept there. She's going to wash the dishes every day, right? So it's like when we were young, you never had to wash dishes. Somebody else, we just drunk whatever was in the cup, and somebody else washed dishes. So a little bonus for showing up in tutoring, and there is a coffee bar down there too if you haven't been to it. So now that I'm I was brainstorming ideas and stuff, and I'm open to suggestions. So some of the problems, things, well, you all know things have changed, right? 2.5 years ago, everything shut down for the pandemic. 2 days before the pandemic shut everything down, and we all had to go to Zoom calls. Everybody remember that? It kind of caught us all by surprise. 2 days before that, something happened in class, which has not happened since. And I think it might have to do with Zoom calls. It used to happen all the time. And that was somebody saw something in the job posting, asked about that when we got to the classroom. So I got out the little lesson plan for the day, and we went over what was in the job posting. Like, well, we were going to go over something that's written in the textbook. Let's go over something that will get you in the door at a nearby job. That used to happen all the time, and it hasn't happened in 2.5 years. That's the big example. I wrote down. I had a long list, and that was the one I thought y'all would understand. Right? I'm pretty sure Zach was here before then, but Zach was here on his first degree before then. But everybody else, I believe, started after the pandemic. So you've always been on calls, Zoom calls. Did you even know you could do that? Remember that you could do that or realize it? Any comments from the chat?
No, no comment.
Okay. Yeah, it's that used to happen like all the time, several times a semester. And it hasn't happened since we went to the. It's just one example of the changes. And I'm starting to feel like I'm kind of following somewhere and keeping an interest. Is everybody following along your class examples? Or are you doing that? You're on the Zoom call.
The class examples of you coding up there?
Yeah, when I'm writing the code, are you following along?
Oh no, that was the example when you said the homework.
Okay, yeah. So
Yeah.
So working on your homework this is an active subject, right? Like when you're doing the homework, you probably jump over on YouTube, find a tutorial. Yeah. That's what I do. That's what I'm doing the course examples. I could stand up here and draw pictures, but it's really intended for you all to follow along, which is one of the big things. And I knew nobody was following along because nobody asked questions. Nobody's like, hey, can you scroll up? I missed what was on line 20 and things like that. But that's what you do when you're working on your homework, right? You follow along the examples. Whenever in class, follow along the example. If you followed along last Tuesday's example, that would get submitted directly for tonight's homework.
Was it the zoo thing?
I'm doing the CICD pipeline. Actually, both of them, the Docker and the CICD pipeline. Last Tuesday's example, if you just followed along in class, you could submit that directly. Because I didn't have any extra stuff to do, so we just went through pretty much perfectly what the homework was. You can change the Java application there if you want. So if you're working on homework last Tuesday, or if you weren't here last Tuesday, you might pull up the recording. Everybody knows where to find the recordings, right?
Yeah.
So pull up the recording and follow along what we did last Tuesday, and that was this week's homework. Or that's the one we do tonight. That was last week's homework. When we get to sit this evening, I'm not gonna laugh how similar it is, but you're probably gonna laugh when you see how similar it is to how similar what I have in mind is to what we'll be doing. Okay, let's talk about very much. You'll probably have a laugh when you see how similar it is, because it's not a perfect match like last week's homework, but it's gonna be very, very close. So yeah, that's I'm going to make changes. We're in week 7. It's too late to change any policies in this document. But for y'all, when we're going through those examples, please follow along because that's how we learn the code. That's why I'm doing those. I could do pictures and just explain what's going on in the computer, but that's Grace is shook her head pretty quickly over that one. We learn by writing code. I could also type a lot quicker than that in those examples. And we put in mistakes. When you go look up a tutorial, we see the finished product, polished version. Y'all have seen that. Hopefully you've noticed that. I like to work in the mistakes, at least the most common mistakes, to see how to fix them and how to spot them, because they don't all give us error messages. What I have in my notes. It's been, yeah, that was the big one I copied over from the brainstorming sheet. That it's been 2.5 years since anybody's like seen a topic on a job posting and coming and asked about that in class, and we just did that one instead. Because that's what we're here for. Learn programming so you can do, so you can get a job. If you see something like that, please let me know. Speak up. Also, I'm not sure how I'm going to be changing the policies. Or for those who I'm in upcoming classes, like 8 weeks. I'm currently working on the lectures for April. And the only reason I'm working on the lecture plans for April for something as soon as April is because I decided to change the game engine I use in the SDEV 48 class. Otherwise, I would probably be close to working on lectures for next fall, a year out. So I'm usually working, I have plans going along way ahead. So changing the policy is a big deal. I really like the old attendance policy. One thing I'm going to mention it last week, and I know it's going to come in there is I have to hear from everybody in the Zoom call, like either the chat room or unmute or something. And actually interrupt in order to get the attendance points. I really like the old policy. What it is, have people turn in the in-class examples. We follow along the examples, and then at the end of the semester, you send me your copy, and that's what the attendance points were. The reason I stopped doing that is because when the examples started getting posted on YouTube, started getting posted on GitHub, the obvious place to post code. Sorry about that. Something one of those points, so that he could get his grade up to a C. And I said something. I told him it's just turning in the class examples for following along. Said he didn't have them. Well, a couple days later, he said, "Oh, I found them," and turned in what I had put on GitHub. So he just downloaded the examples and turned those in to get points. So that's why I stopped that O policy. I really like that. I thought that was a good one, but to go back to that, I'd have to stop posting the class examples on GitHub. Speaking of which, did anybody look at the MySQL one that I posted on GitHub? So if you turn that assignment in on time, the example that was in your book for reading from the URLs, websites was fine. The example from every tutorial was fine. But if you turn that in more than 2 days late, you use deprecated code on. I like when that happens in class. So programming languages have one of the things they change on us. We have to stay up to date. So I did I obviously it changed last Sunday on the 24th when Java 21 came out. So uh, we can count on deprecated things working for 2 years, and then they're going to be removed entirely. So there's like a 2 year span to remove it out of there. Y'all may have noticed when you type the URL class in NetBeans, it put a line to it. You strike through text. That means the thing has been deprecated and will stop working at some point.
I remember that you discussed that with me during the example of URL, it was crossed.
Yes. So, and that was actually before the 24th. So NetBeans, well, Apache is the one that pushes that out. So obviously NetBeans changed the week before. But if you see strike through text, that means it's deprecated and you need to go back and update all your own code. And the guarantee you have 2 years to do that, but it's iffy. I still use something that was removed in Java 2. So basically, when Java was in beta testing in 1992, there was a date method before they went to the Gregorian Julian calendars and lots of other calendars, but textbooks written in English, I'm going to talk about the Julian calendars. But our dates that are more specific has been that way since like 1990, the early 90s. But I still use the one that was deprecated in the early 90s and installed. The URL one is probably going to be the bare minimum because there might be a security loophole there. There might be a way to security. They put some temporary patches in place to carry through that 2 years, but there is a security hole there. So that one we can count on. It was deprecated on September 24th, 2023. We can count that will entirely guarantee that's going to stop working on September 24th, 2020. The soonest they can get rid of it. But obviously reading from URLs has been a big thing for many decades. So they need to give that 2 years so people can update their code. So the non-deprecated version is on the repository for this class. If you want to look at that, it's called Homework Assignment 34. You'll see the class. I'd like to go back to the old policy, but it would require stop putting the class examples on GitHub, which I don't know if anybody looks at them or not. I would like if y'all can give me some feedback, because I'm kind of feeling like I dropped the ball, failed you a little bit here, putting the class together, I don't feel like I did as well as I could have done over the last year, and it's been building. And if y'all have any feedback, what would you like to see in the class? What would you like to see in the class? Let me know. If you like the sound of that old policy, let me know and we can go back to that. I've heard a couple ideas. Some of them have more interactive stuff, like there's Kahoots. Anybody use that? It's the polling thing. See head nods there in class. Those on Zoom call, have you ever used that?
Wait, did you say Kahoot?
Kahoot, it's a polling thing.
Oh,
So,
yeah.
Zoom also has that built in, so we could use those here. And then kind of get some questions like, what does everybody think, should it be option A, B, or C, and have an example code before we type it. Another idea, I might try to give it a test run in here next week, but I don't know if we'll be able to, because next week's multi-threading and parallel processing. And the idea is to go to Riplet IT and all of us log into the same one, so that when we're doing our class example, I'll call on people to write lines of code. Like, you want to get the next line of code? Try. And obviously, for a classroom example, writing the wrong code in a situation like that's a good thing. Then we can explain it, see how to fix the errors, and do all that stuff. Make adjustments on it. So I'd like to try that, but next week is about multi-threading and parallel processing. And I don't know if we can do multi-threading and parallel processing. They probably only give us one thread on a single core, is my guess. I haven't checked. If I had an online IDE site that big, I would not be giving people multiple cores to work with. So I don't know if we'll be able to do that example or not. But something where we can work class examples together. That required sharing, like take 15 minutes every Monday or Tuesday, the first day of class each week, and tell your classmates something you learned in code. Did you find a good tutorial site? Did you find a good joking site? Which I did find a good joke site. Okay, yes, thank you for that. And I didn't see your message at first in the chat room, Joseph. Yes. So we're gonna talk about hash tables here very, very shortly. I did find oh, let me turn the screen. I did find a programming humor site on YouTube, which YouTube suddenly got really, really bad. All weekend, YouTube started recommending to me videos of women trying on clothes. I'm like, in the 15 years I've been on YouTube, what would possibly make the algorithm think I want to see that? I was a little annoyed, so I started hitting the report button, and that way at least the person, a paid human employee has to waste their time on it. Because I don't think it was inappropriate ones. I think it was just people trying on clothes. So this guy, programmers are also human. I haven't seen all of his videos, but the ones I watched were very, very funny. Some of them absolutely hilarious. The Emacs one is great, and the PHP dev is great. But it's clean humor, so I can share it in the classroom. That's the biggest problem. I used to always send out joke ones, but I spent like 3 days trying to find a site that had all clean jokes so I could share it in class and leave that site. And it's been a year and a half since I found clean jokes that I could share in class again. I haven't watched all his stuff, but all the ones I watched were clean jokes, and they were absolutely hilarious about programming and stuff. So something like that required sharing. Did you find a YouTube channel or a great joke on Reddit programming humor? Something relevant that is worth sharing to your classmates. Conversation. I know you're all heard me talk about it before, that thing discussion boards are supposed to take the class place of. In the traditional setting, you and your classmates would all show up to campus at the same time, walk down the hall together, sit in the class, then after class, walk back to the parking lot together. Those conversations, those informal things do contribute to education. So maybe try required sharing or something to work that in. Check out that channel, it's pretty fun. Everything I watched was pretty funny and it was clean. I apologize if you click on one and he did do some dirty jokes, because I watched a bunch and there weren't any dirty jokes in the ones I saw. So I apologize if there is, because I did not see everything that he made. Yeah, good tutorials like you found, YouTube channels, alternate syntax, what we see. There's always more than one way to do things. Yeah. Yeah, go back. Considering going to my old idea of actually submit the thing, because we're computer people, right? There's reasons why we're all in this class, and it's not because we like to talk. So that whole having to talk, I don't want to do that in general. But I have heard every one of you have thoughts. I know you're capable of talking or typing in the chat room, right? You're not the as far as I can tell, nobody in this class is crippling Chinese, right? That if I'm following your name to answer a question, you're not going to jump up your chair for a living and a ball in the corner. Some people are like, people coming down peace. I don't want that to be the general policy, but have to make some changes. I feel like the world has changed. I think we're settling into this now, right? just kind of seem like what the world's gonna be like going forward. So we need to figure out what works best. I have some ideas. It's been a long time going over that. But please, if you have any ideas, please share them with me. I'll see what I can do about it as I revamp the policies. So, okay, somebody else suggested that, something Marlene does, and yeah, I knew Marlene does that, so it was on the list. How breakout rooms to split up into groups.
Yeah,
You like that idea?
it was nice, but then near the end of the point, everyone was just silent. And which kind of was a little unnerving and I kind of just went back here, but I get it.
The novelty is worn off, which is a big deal with this class, to be honest. The novelty is worn off. Starting to see why programming often pays six figures. The novelty wears off, and then you see the aggravating points. Of like, why won't this code work? And you know, on the desk. That doesn't show up in the and not so much in the 140 because it's still new and novel and interesting. We're making all this stuff happen. Now we're at the point where it really starts to work. And for the rest of your classes, you're going to are more that you get a better understanding of why it's a six-figure job. The aggravating points. So try to find something that try to find what you enjoy, little victories, right? When one method works, celebrate that, and don't wait till the end of the program because you're gonna be so utterly frustrated if you wait to the end of the program to celebrate. It's just gonna overwhelm you. Jobs that pay a lot for a reason. So at this point, people are starting to see that the novelty of it's wearing off, making a computer do something so fascinating in 120. The first time we see it, it's like, oh, this is awesome. The computer just does what I tell it to do. So, yes, please let me know if you have suggestions, because yeah, that's the goal, right? Interaction, doing stuff. We're missing that interaction on Zoom, and it's not just class, right? This week I'm in curriculum committee meetings all week long. And they are not at all like they were before the pandemic or in April. If anybody had me in class when I took the 3 days off to go up to the hotel in Indianapolis. And instead of all sitting patiently on a Zoom call, waiting our turn to speak, we were all in the same room yelling at each other. It's very, very different. So it's not just the classroom, and we need to figure out how to adapt. And I'm not going to figure it out by myself. But what would you like in a class? What do you have that I could give a try to? So on to the 9th. Ever heard the word hash? Thanks. It's part of standard English anymore. The hashtag, which that's modified slightly. Hopefully it'll make sense what the hashtag is in a moment. In programming, it's a hash key, but I guess that doesn't blow off the tongue really well. So when Twitter had to do the fastest possible way to find any piece of data stored in its massive warehouse. Right? Twitter is not just one server, something that big. There are lots and lots of servers storing short messages. And we need to be able to find them and then get them across the internet in a couple of milliseconds. So we need the fastest possible way to retrieve anything. And that's where hash comes in, hash tables. So what a hash is everybody knows key value pairs, right? Pretty sure everybody would have seen dictionaries in Python, where we treat it like an array, but instead of indexing it with a number, we index it with a string, which is very, very useful. So the key or the index in an array is the key. Right? We say we want index 3. That's the key to find the value stored at that spot in the array. Something more useful so we don't have to remember every single piece of data. And in particular, key value pairs where the key is generated from the value. And table is because we can think of it like a table. We have our keys and our values. So maybe our program, I'm going to oversimplify for the picture. Has everybody seen that default to print in Java? Right, you forget to put a string there, and then you get that package.class add, and then some great big long string, hexadecimal string. That's the hash key. So maybe we wanted to put a 4 in our program. We store that. We want to store that. So there's going to be an algorithm. To keep it simple for the example, let's say our algorithm is 3x plus 19. So we want to store the value 4. We need a key so we can refer to that. If it helps think of it like the arrays in an index, but the simple indexing is not. So think of it like the index is in an array, but the simple indexing isn't going to work. And strings like a dictionary would be too complicated because we don't want to spend a whole bunch of time coming up with all those strings. So we're going to use this little math equation here to figure out what the key is. We want to store 4. So then 3 times 4 is 12, plus 19 would give us 31. So then that gives us a key of 31. And then the key 31 stored with 4. And we need a 9 after that. So we plug a 9 in. 3 times 9 is 27, plus 1 less than 20, 47, 46. So our key is pulled from an algorithm this way. We just want to be careful because certain things, when it gets more complicated, things could cause keys that we could clash, right? Like we took character values. Capital A, lowercase e. Those 2 characters, if we just did that, right, 65 plus 101. Those are the 2 I have memorized. I count from capital A and lowercase e if I need ASCII code. We add those together and say, okay, the key for that value is 166. But with this algorithm, if we did BD, capital B, lowercase d, we'd get 66 plus 102. No. I think I meant that. I did that backwards. Sorry. Put the BE up there and 80 there. So then we get 66 plus 101 or 65 plus 102. And we end up with the same value if we just do something simple like that. That would be that would cause a conflict because then if we ask for key 167, which one do we get? Which string of characters do we get from that? So they're usually complicated algorithms. And in Java, or in general, most every other programming language we would have where we use hash tables is a similar thing, not Python because we don't have direct memory access in Python, but anything where we have memory access. So not Lua either, because there's so much to have in the background. But things like the C family where we have access to it, this becomes the location in RAM. if we print our object without overriding the two-string method and you get those hexadecimal values, 9 hexadecimal characters, that's kind of a big number, right? It runs through a very complicated thing. Some very, very smart people who spend a very, very long amount of time making sure, trying to minimize the conflicts. that key becomes the location in RAM. Everybody's seen a RAM chip, right? I'm gonna pull up one in div form. AD28C256. So this is a ROM chip, but it's same thing. So we have those. This particular one has the pins going down each side. I just did it this way so we can see it. We have so many pins down this side, same number down up the other side, so they're kind of symmetric. The way it works, and RAM chips work the same way, so let me circle these. So like maybe these are the address pins, and these are the data pins. When we want something off that RAM chip, we just activate that in RAM. So like 31 there is one less than the power of 2, so that's really quick. 31 is 0, 1, 1, 1, 1. It's one less than 2 to the 5th power, so if we add 1 to it, we'd get 1 and a bunch of zeros. So a 5-bit address, we would just turn on, send the low signal to 4 pins, 1 pin, and high signal to the other 4. So we would immediately feed that electricity, not ones and zeros like we type, right? Actually flipping the switch on and off into the address bar, and the data immediately flows out the other side as quickly as we can do, like as quickly as electricity flows. So essentially with the hash table, we're moving at the speed of electricity. Notice how that table looks an awful lot like that chip, right? Let's see. I should clear these pictures so they're not in the way later. So using a dip chip, there's lots of different. That's dual inline post or dual inline pins. If I drew a picture of one of those, 4, 5, 1, 2, 4, 5. So let's say this is our address pins over here, and this is our data pins. If we ask for this in our code, we're basically just feeding in 0, 1, 1, 1, 1. We feed our key directly into the address pin of the RAM, and then our data flows out as quickly as electricity can flow through that chip. Super, super quick. The biggest drawback on them is coming up with the algorithm complex enough that it's not going to crash on itself, and it's not going to end up with duplicates. You remember way back in module 1, and we're talking about storing things in memory. We had a variable called X, we store a 3 over in RAM. If we gave another variable called Y and store a 3 and put a 3 in Y, what happens in RAM? Can I remember? If we have 3 stored to one variable, we create another variable and try to put the same value, the 3, into that second variable, what happens in RAM?
Well, I guess there.
If I heard you correctly, I think I just heard the last out of the sentence, but I believe I heard you correctly. It's already in RAM. We don't need to store it again, right? That's where the hash key comes in, because we turn Actually use the one that's on the table. We turned a 3 into some address in RAM. This is not the algorithm Java runs, it's simplified for the board. But 3 times 3 is 9 plus 19. We'd say it's in address 28. So we go to store it in RAM and say, okay, that's going to be at what is 28? 0. We need 16 plus 8. This is 24 plus 4, and then another 0. So we do this, see that that value is already, there's already something at that spot in RAM, and we don't need to store it again. That's part of the really, really good memory management in Java. And hopefully you can see here how, if I draw like the dual inline post sort of chips, we can see how what we put in our code, what we put in our program corresponds explicitly to the circuit. So basically a hash table is as good as we can get as far as speed. There's some drawbacks and times when others would have other advantages over it. But that's the idea of what a hash table is. So all of the tweets on X now used to be Twitter. But those years and years and years worth of tweets that we would find any of them from a hashtag, that hashtag was just a particular value that we turned into a numeric address. And that numeric address had what server it was located on and what spot in RAM it was on that server. So we could pull up any tweet immediately. That's how it searches so quickly through Twitter. And why this is now part of the English language. Why it gave us one more word for that symbol above 3 on the keyboard. There's already a bunch of things we called that. Any questions about that? That one's going to be important. And obviously where the importance shows up is not going to fit in the time constraints of a classroom. It's probably very confusing overall right now. Like, I shouldn't ask, are there any questions? Because I know there are questions, but you might be having trouble vocalizing. Do those words all make sense? And again, this is data structure, so 10 years from now, you're going to look back and be like, oh, now I get why I needed to do that instead of just run through whatever arbitrary way at. So the other big one that is really, really useful for so we previewed a little bit last week we saw the set data set or set data type in Java. And you'll remember how that was abstract. We can't instantiate a set. We have to choose particular types of sets. And pull up the example from last week if you don't remember that. I think it was this one. So we talked about we got down to set. We couldn't just say set of some data type equals a new set because set is abstract. We don't know how we're storing the data for that set. The only rule for a set is that a set cannot have duplicates in it. So a hash set works great because if we have any duplicates, as soon as we turn that in a hash key and try to put it on RAM, something's already there. So we know that we already have that. It's really, really quick to do that. But our other option, if we look at it briefly, we didn't type in the example, was a tree set. So it usually comes down to a choice between these two. When you get into data structures and you're working with programs that are so big that you have to start worrying about stuff like that. Does a hash table fit your situation better, or does a binary search fit your tree? So everybody know what a tree? Does everybody know what a tree is? Got head nods
Yeah.
in the class.
Yeah.
Yes, there. Jenna, Larissa, Zach. Y'all are familiar with trees, right?
Yes, sir.
Okay, so, right, we have our root terminology. Then we have branches that come off of the root. And when we get to the end, let me do some extra ones here. When we get to the end, so like this one, and this one, I'll do like 5 off of here. All of these here at the end, those are called leaves. Which is almost always misspelled, right? Everybody knows it. Everybody remember how to spell leaves from elementary school. Leaves. For some reason, if you're ever in a computer situation where you need to access the leaf on a digital tree structure, people almost always spelled it with the FS, spelled it wrong. I have no idea why. So our basic tree structure, and then what we see binary. This one wouldn't quite fit this definition. We can tell from the first word binary indicates how many branches we have, right? Let me erase this picture. That was just a reminder of a tree. A tree with at most 2 branches off any node. So 2 branches off any node, there's our binary part. And ordered with small to left and big to right. And I'll put some quote marks around small and big. If we're talking numbers, then smaller and bigger would fit a lot better in that sentence, right? But whatever the order is, the lower value goes to the left on the tree, and the bigger value goes to the right. So I have some numbers to use for an example, and I did go digging through videos from past semesters, because as many times as I've talked about binary search trees in class, I have discovered that not all data sets are the same when it comes to the pictures. Sometimes they don't make very good pictures for class. So camera over just a little. So I dug through and checked old videos to find a set that worked really well for the picture. So these are the numbers that we have: 7, 3, 19, 2, 11, 5, 13. It has nothing to do with them being prime numbers. I just now realized those are all prime numbers. That must have been what I had in my mind that day. Those were some I pulled from a class earlier. But the way they're scattered, right? Start kind of in the middle, then we go way down to the beginning, up to our biggest number, then back to our smallest number, and that's the order they come in at. That's the part I was looking at previous videos for to find numbers, and I just now realized those were all prime numbers. So that must have been on my mind when I did it. So what we do is the first element that we have becomes our root. So we'll have a 7, and then smaller things go to the left and bigger things to the right, which were in numbers. So the smaller and bigger is obvious. But I already told you on Thursday we're doing a payroll example. You might see the data set I sent out. Do that science step. Probably not. Grace looks confused. Did anybody on the Zoom call see a data set I sent out today?
No.
Yeah, okay. I was asking because I didn't know if, y'all look there. So on the homepage where I do those little notes every week, which you probably won't read, I didn't, they're random, a random summary of what I have in the notebook. I just step over where the thing I'm holding up is on the camera. A random summary of what I have in the notebook each week. I put those notes on the homepage. And I thought maybe this would be a good spot to download files from. And then I started questioning that. So I put it on that home. I put the file there for Thursday's example. I put a file we'll need there to see if anybody's seen it. And apparently nobody saw it. So I didn't need it. I think it might be a good place to do that, but I'll have to tell everybody that that's where you can look for any files we need. That's for Thursday, but we'll have employee objects. What's the order of our employee objects? Are they ordered by seniority? By alphabetical order? They ordered by birthday? What do you think, Larissa? I saw you on mute for a second.
I was gonna say maybe by alphabetical order of their last name.
That would be a standard way to do it, but maybe is the key point in the answer, right? Because we don't
Yeah.
know. So whatever smaller and bigger is it's for the situation. For our example and picture on the board, we have numbers, so smaller and bigger is obvious. So we got our first element, next one's a 3. Smaller goes to the left. So 7, it's a binary tree, so we can have 2 branches off of 7, and we'll put a 3 over here to the left. Then we've got 19, that's bigger than 7. Which way, where's the 19 go? To the right of which one? Because it's a binary tree, so both of these will have 2 branches coming off of them. Yes. We always go back to the root. Always start at root. So we got the 3 in there, so we go back to the root. Next one's a 19. It's kind of like linked list. Remember how we just had that next variable? So the only thing we can do is go to the beginning and then keep going, and we have to go back to the beginning every time. Like a linked list, we go to the beginning of the list and just keep hitting next till we got the null one. Whenever we hit a null element, that's where we know the next one goes in. Same thing here, only we organize it a little bit. A 2, so we go back to the root. Somebody on the Zoom call. Joseph, which way do I go to place a 2? Either
Left.
left. Yes. So we go left. Well, there's a node here, so we have to decide again. Which way do I go at this node?
You go, I assume, left again, but
Yes. It always follows that pattern. So this repeats at every single node.
Mhm.
So we go left again, and we hit an empty branch. So that's where our leaf goes in. 11. So we go back to the root. Jenna, you want to answer this time? Which way do we go?
I was actually just about to write in the chat. So is it the left subtree is less than and the right subtree is greater than? That's the property. That's how the flow goes. Okay, then you go right if you're going.
Yes. So right to a 19, and we're looking at 11. Now it's right.
Oh,
The 11.
hold on.
So you had it right the first time. Somebody else want to help her out?
Would it be
Yes.
also left again?
Yes. Did you hear them?
It's left.
So we can do the same thing.
Yeah.
Like you said, at first gen, it's less than or greater than. So 7, 11 is going to be greater, so we go to the right. And then we're at the 19, 11 is less than, so we need to go to the left. That makes sense? I was actually watching the chat room. I was expecting you to just put something in the chat room instead of answering, but which is acceptable. If it's more convenient for you to type in the chat, that is perfectly okay. Yes. So like if dogs are barking, if they get all excited when they hear your voice and start barking too, then unmuting isn't the best option. Which, yeah, if you've been sitting there quietly for 45 minutes and you suddenly talk, the dogs are going to get excited. Guaranteed with everybody's dogs. What's next? 5. You want to tell me which way to go on this one, Grace? So we've got this. We're up to the 5.
So you go to the left. And then to the right.
To make room because there's more coming to this picture. One left. You want to tell me which way to go, Larissa?
Is it 30 or 33 or?
13. Sorry. I do the little flags.
Oh, you're
I put
good.
letters on one.
Would you put it at the very end?
But there's several ifs because these are all nodes in a binary tree. So at this point we have 1, 2, 3, 4, 5, 6. 7 ends that we could go to. So we want to walk through each one. So we start at the root.
Mm-hmm.
Which way do we go? Left
You're
or
gonna
right?
go left.
So bigger thing, smaller or less than goes left, and bigger goes to the right.
Okay, so it's gonna go to the right.
To the right, and then from 19, will it go
It's
right?
smaller, so it's gonna go to the left. And then that's smaller than that, so it's gonna go to the left of 22.
Oh, that's an 11. Sorry. I read it like that. That one's
Okay,
an
so
11.
then it will go to the right of
Yeah.
11.
Yes. So you had the right idea. It's just my awful handwriting. This one I could give like advice. On a very important math test, let me write it big enough where y'all can all see. Everybody's been in a math class before, right? You know, those little mistakes happen, like sometimes 2 + 5 = 8. That's why math teachers give partial credit, because that happens to everybody. But on a very important math test, 301 times the natural log of some number showed up. I wrote it like that. I wrote my 1 and my L the same way. So with those 2 vertical lines right there together, y'all can probably figure out pretty quickly what happened on the next line, right? I don't know which one disappeared, but one of those disappeared, and that messed up. That was like in step 2 or 3 of a problem that had 30 or 40 steps. Like in the 300 level math class, 400 level math class. It was up near the end. But a very important math test, that mistake happened. So after that, I always do my 1s with the serifs on them, and my L's all curly like. There's a 2 next to the 1, so you can see that, Larissa. You see how I write them different if they're both on the board.
Okay.
I make the 2s very curly, but it's yeah, I guess something y'all can watch out for too, because vertical lines are used all the time. It's a really easy symbol to draw, but we use it in more than one way. Or to put it in programming terminology, we overload the vertical line in our written language It shows up in lots and lots of different uses, so that's our binary tree. There's a slight typo in yours. Really, really close. You want to try that again, Jenna? Or somebody else want to put it in there?
Wait, what happened?
Oh, no worries. In the chat room, she drew the binary tree in the chat room.
Oh, I was wondering like why she put a 7. Like, and then I opened the chat. I'm like, oh, now I see.
Yes. So you're right on. I think you actually hit. I think that was a typo. So at the third branch, 2, 5, oh, actually, let me see if I can type this in the chat room like you did. Whoops. Eh. Let me try that again. How'd you put the line break? Is it alt enter?
Press
Shift
shift.
enter.
Shift enter. Okay. Usually it's alt enter. Or in spreadsheets, it's alt enter. I've never really done it any place other than a spreadsheet. So
Sometimes you have to do that in chat rooms as well and other places, so.
then we have a couple of these. Enter here is 3. Oh, whoops. Sorry. There, 2, 5, 11. Then we go that way. It almost lines up. The 5's in the wrong spot. Does that make sense? I think that was a typo. It sounded like you understood the concept when you were talking. But I also, that was very, very difficult to draw in the chat room. You can annotate as well. If you want to draw pictures like that, you should have the annotate button. Sorry, never mind. Not if I share the screen. Usually in this class, we're doing screen share. So when there's a screen share, it's a lot easier to just annotate it. So I'm going to empty off these, erase these that don't have anything. So that's our binary tree, binary search tree. Is it okay if I use colors for the next little section? Let me zoom in a little.
That's fine.
So did anybody notice I put in the definition ordered by or ordered with? I've been very careful to avoid the word order since then, because that's where binary search trees really come in handy. Oh, and like we saw with linked lists, that is just a data field we'll put in. We'll make one of these this evening, and we have a data field that points left that says called left and one called right. And then we just do less than, or we're in Java, so we'll probably have classes. Y'all remember that compare to method and interface, implement comparable. Then we have the compare to method, and we'll say element dot compare to and move either left or right. So we define what smaller and bigger are. So now what is the order that we go through this in? Because there's 3 different ways we can go through it. we can do what's called postfix. We could go through it in order. Or we could go through it in what's called prefix. And now that I write those on the board, I realize I probably should have put pre at the top and post at the bottom. That would have made a lot more sense, but I'll start down here at the bottom with pre. So prefix, we go through in the order of node, left, right. When we go in order, well, that's kind of what's up there. We go left, node, right. And postfix, we go left, right, node. That's a very, very important thing. As you move forward, please write that down. If you're not the type of person that takes notes, please write those things down. You might want to put pre at the top. That would make more sense the way Americans organize things, but postfix is better for machines. Anybody ever used a TI calculator? When you push the buttons on your TI calculator, so not the programmable ones, not the ones where you basically have text entry, but up to a TI-84, right? Things go in and we type one digit at a time, or a basic one. Actually, most calculators do this. I just refer to the TI one. This one, our basic, just a little basic calculator. I can turn on the camera for that. We type 5. If I 5 plus 8 equals, so I get 5 plus 8 equals. But you think real hard back at the beginning of the semester, one of the subtle notes. So when a machine does stuff, it has to know what operation it is, right? We have binary operations and unitary operations. Some things take 2 numbers, some things only take 1. So the machine has to know what operation it's doing first. So that plus sign has to make it around in front. And it uses a binary search tree and postfix. Notice in all 3 of them, left and right are in the same order. And then pre has node first. In order has node in the middle between left and right. And post, meaning afterwards, has node afterwards. So that's how we travel through the tree. So if we start here, we always start at our root. We come in. I had the red marker in my hand, so I'm going to do post first. So postfix, we want to go left as far as we can. So we'll go, we can keep going, and then finally we get to something on the left. So we'll go ahead and record that number. 2. Next we want to go right as far as we can. So we go back up our tree because we're on a left branch, but now we're heading rightward. There's a node, but we need to go right as far as we can. That gets us this 5. We can't go any further right, so we'll use that one. Well, can't go any further right. We already went left. We can't go left, can't go right. So now we're ready to come around and grab that node. So we get a 3. We'll continue around, going right. We've already gone left, so we'll go right as far as we can. There's a 19. Check our order. Looks like we can go left, so we go left. Can't go left any further, so we'll take that one. We can't go any further left, so that's the one we want to grab next. 11. Then we'll go right as far as we can. There's only one place to go there. We get the 13. Can't go any further right, so we have to come back, backtrack a little. We hit this, we can't go any further to the right, so we need to grab this node. We already went left, we can't go right. So the only thing we can do is grab that node. Am I still on the board? Yeah. Can't go right, so we'll come back up, and we haven't grabbed this node yet, so we still need the 7. So notice how we start with a low number. It gets bigger. Then we go back to a small number and gets bigger and bigger and bigger. And then it goes back to a small number. And that's as our tree goes larger, that's how it goes. We start small. Am I on the board still? Yeah. Start small. Then we go bigger. Then we get small. It's like a wave. We start small. And we slowly get bigger. Then we drop back to a small number and get bigger. Drop back to a small number, and I'll do this one more time. And then we get bigger. So this is how we go through our numbers. So notice it kind of changes our order. It's not in order. In order is obvious. That's going to say 2, 3, 5, 7, 11, 13, 19 in order. But if we have this up and down motion, then we also should have the ability to jump a couple ups over without going to the down part. So it gives us a different order to traverse our numbers in. We don't have to just go 2, 3, 5, 7, 11, 13, 19. There's alternative orders we can go in. So in order, these 2 pictures will go quicker if I can remember where I left the other markers. There it is. In order, we go left as far as we can. Then we go back and grab the nodes that we pass, and then we go to the right. So we come into the root. We can go to the left, so we grab a 2. The left, and well, we already went left, so now we need to go back and grab the node that we passed. We passed a 3. Left node, then we go to the right, grab that 5. That's as far left as we can go. That's our entire left branch. So when we go back and grab that node that we passed, 7. Now we have to go to the right. So we start going right, but now we have a chance to go left again. So anytime we have a chance to go left, we go left as far as we can. Which gets us over that 11. We grab that 11. Actually, we would think of that as a binary tree or another branch here. We couldn't go any further to the left, so we come back, grab that node. Then we go to the right. Can't go any further right, so we come back and grab the node, and there we are at the 19, and those all went in order, right? 2, 3, 5, 7, 11, 13, 19. The order we're used to. We start at the beginning, we start at our lowest value, and then we just go up. We don't have that back and forth. Anybody want to take a guess at what prefix is going to look like? As far as those arrows drawn on the left-hand side, right? Postfix started low, then went up, low, and then up, and we take it in little segments of up and down. In order just constantly goes up. That's the one we learned in kindergarten. Any guesses on what prefix is going to look like afterwards? I'll start drawing it, but feel free to speak up. We come to our root. We want to do our node first. Well, our root is a node, so we'll grab that. Probably shouldn't have a big red dot there. So we grab the 7. Then we go to the left as far as we can. No, we start going left and then we grab nodes. Here's a node, we need to grab it on the way. So we grab that 3. Node, we started going left and we had to start over again because we hit a node. So we got that node, so we'll continue going left. Gets us down to the 2, and I'm going to draw the big dot up here, indicating we grabbed it as soon as we found it. Got our node, we can't go any further left. So we start going to the right. Come around, we already grabbed the 3. Keep going to the right, there's our 5. This kind of made the picture difficult. Then we're coming back. Come back, we already grabbed all these, then we go to the right. First node we hit is a 19. Right, we finish the left, then we start going right. Well, we'll go left, grab the first node we see again. An 11. And can't go any further left, so we have to go right, which gets us that 13, and that is all of our elements. Nobody spoke up and said anything, but does that match what your guess would have been? So 7, 3, 2. So we start up and go down this time. So with the arrows, we have something high and low, depends on what our root is, and our root was just the very first one in the set. So that's kind of arbitrary how high we are, but we start there and then we go down and then we jump straight back up to 19, to a 5, and there wasn't anything to go off of the 5. So we kind of get this one, I don't know, picture a 4 in there. A 4 would come after that 5. Hopefully you can extend the picture of the tree and see where a 4 would go with node left, right. Then we're back up to a 19, and then we go down to an 11. Then we go up and down, and see how once again we have that up and down traversal. So again, preview of what we're going to talk about, one we're going to talk about after break. If we can traverse through this tree in an up and down fashion instead of that numerical order we learned in preschool, we should also be able to jump between like the crest of those waves. Or like a surfer. We could ride those waves and stay on the top of the waves, and we don't necessarily have to go to the bottom and look at all the stuff down there. But it gives us other orders to traverse through. That's the idea of a binary search tree. So it's close. It was close. Yeah, that one's a little unpredictable. We do have to catch every node. In the chat room says was wrong at this. A second node tried to say 2 instead of 3. But you may have noticed I did the same thing in the picture. I tried to pass it. Because as soon as we hit a node, we start over. The difference between these, notice how, before we take our break here, I can zoom in on these pictures a little. Here, they're all independent pieces of data. They're all separate. And here we have left and right variables in our object, but it's like that linked list when we saw it, right? That next pointer. We have each data element points to the next element. So these are all kind of independent, and if we grab this piece of data, we work with it, then over in our code, then we have to go back to the table to get the next one. With a binary tree, we grab this piece of data, and to get to the next one, we just follow that pointer. We're already pointing at the next one. So that's the difference between them. Here we have to keep jumping back and forth because until there's an extra step to jump over to the hash table. So the choice between them would be how much you jump between them. If you're constantly looking at all the data, jumping back and forth between different ones, you want to follow the pointers. Because every time you have to go back to the table, you have to empty what's in your registers, load in something else in the registers, figure out what that's going to be, and then load, and then empty registers again. So there's like a refresh every time with the hash table. It's much faster because we're working at electronic speeds. But this cuts out a step every time we switch between data points. That went 5 minutes longer than I meant to. It's gonna take a break a moment ago, but we were so close to the stopping point. 10 minutes sound good? I got head nods. All right, so my clock says 7:22. We'll get back to it at 7:32 and look at heat. Finally, I know some of y'all have been seeing me write that word on the board for several classes. We'll look at heaps and then graphs, and then we'll code up a map, which is what's in your homework assignment. See y'all in just a moment.